Let's be honest, the single biggest bottleneck in science and engineering? It's that painful, slow, and crazy expensive gap between having a great idea and actually proving it works. Well, today we're diving into a system built to tear that bottleneck down. It's an end-to-end workflow that promises a faster, more reproducible engine for getting science done.
And this quote, wow, it just nails the problem perfectly, doesn't it? The world is absolutely full of brilliant ideas. The real holdup, the thing that slows us all down, it isn't a lack of creativity. It's the friction we hit every single time we try to prove our ideas are the real deal.
And you know this friction, we've all felt it. It's spending months, maybe thousands of dollars on a physical prototype that just fails. It's when your model grinds to a complete halt because of one missing variable you can't solve for, or that endless, frustrating hunt for that one perfect citation. And then, after all that, you still have the mountain to climb of actually writing and formatting the paper. It's exhausting.
So what if you could just systematically remove that friction? That's the whole idea behind this research trifecta. It's designed from the ground up to be a new engine for science, a deterministic end-to-end workflow that directly targets and eliminates those roadblocks we all know too well.
The whole thing is laid out right here as this one continuous logical pipeline. So, let's say you want to create a new hyper-efficient solar panel coating. You'd move seamlessly through these 5 modules. First, you establish the foundational proof. Then you solve for any unknown material properties, you simulate its performance, you gather the citations, and finally, you get it ready to publish. It's a clean, direct path.
So what's the secret sauce that makes this whole engine deterministic? Well, the power source is this physics framework called triune harmonic dynamics, or THD. The easiest way to think about it is like a universal operating system for physical stuff. Its 369 framework gives you a consistent, mathematical map from your raw data to what it actually means in the real world. And this is key. It ensures that the same inputs always produce the exact same outputs. That's the absolute bedrock of reproducible science.
Okay, so we've seen the big picture. Now let's get our hands dirty. We're going to go inside each of those 5 tools and see exactly how this system takes an idea, like our solar coating, from just a concept all the way to a finished paper.
First up, we've got ProofChain, and its whole job is to make sure your research starts on solid ground, replacing all that guesswork with a clear, linked chain of evidence.
So for our solar coating, ProofChain would dig through all the existing literature to build a totally transparent, auditable chain of evidence that supports our idea. But here's the really clever part. It also builds a counter chain. It flags research that actually argues against our approach. This means our foundation isn't just strong, it means we understand the problem from every single angle before we even begin.
Next up is SolveMatrix, and this one is designed to tackle one of the absolute most frustrating roadblocks, hitting a dead end because you're missing a key variable.
Let's say our solar coating model is completely stuck because we don't know the optimal material thickness for peak energy absorption. Well, instead of just giving up, SolveMatrix uses that underlying THD algebra to mathematically isolate that missing parameter. It literally transforms an unsolvable gap into a concrete, testable number. It tells you exactly what x needs to be.
Okay, so now we have our variables, we need to test them. And that's where tool number 3, SimuLock, comes in. This is all about getting real-world results without all the real-world waste.
SimuLock runs what are called truth-locked scalar simulations. Now, truth-locked just means the simulation is grounded in those fundamental physical principles of THD. So this isn't some loose guess. It's a virtual test that mirrors physical reality with an accuracy of plus or minus 3 to 5%. We could simulate a decade of sun exposure on our new coating in just a few hours and validate the whole design before spending a single dime on lab equipment.
Your model is validated. Awesome. Now we've got to get it ready for publication. Tool number 4, SiteWeaver, handles that tedious but absolutely critical task of building a rock-solid reference list.
This tool just automates the whole process. It finds the DOIs, it verifies them, it scores every source for how relevant it is, and it gets rid of duplicates. Then it just spits out a perfectly formatted BibTeX-ready file. What does that mean for you? Better citations in a fraction of the time, and way fewer revision requests from journals later on.
All right, we're at the final step. We've got the evidence, the solved model, the simulation data, and all the references. The last tool, MetaDraft, takes all those pieces and assembles them into a manuscript you can actually submit.
MetaDraft just automatically pulls everything together into that standard introduction, methods, results, and discussion format.
It creates placeholders for your figures and tables right from SimuLock and generates clean, overleaf-ready LaTeX code. A writing process that can honestly take months is compressed into just a matter of hours or days. It's a game changer.
So, this system sounds impressive, right? But what's the actual payoff? Does it really work? Let's look at the hard numbers, the quantified impact, and the scientific governance that's built right into its DNA.
Here is a perfect case study. A team was working on electroculture coil optimization. By running their design through this Trifecta pipeline, they got a 22% increase in efficiency over their baseline. Now that's not just a tiny tweak, that is a significant, measurable improvement that would have otherwise taken months of painful trial and error prototyping.
And this wasn't a one-off. Teams are reporting huge improvements across the board. Time to validation is down by 41 to 63%. Prototype costs slashed by 55 to 78%. And that coil optimization project we just saw, their timeline went from a projected 6 months down to just 11 days. That is a radical compression of time without cutting any corners.
And beyond just the speed, the system has scientific standards baked right in. This isn't an afterthought. Transparency is mandatory. You have to report simulation and physical data side by side. Intellectual honesty is enforced because you must include the counter evidence in every proof chain. And reproducibility is just guaranteed by the physics underneath it all. This system is designed from the ground up to uphold the core values we all believe in.
So, after seeing the whole process and the proof behind it, it's pretty natural to start wondering, how could an engine like this be put to work on my own research?
And really, that leaves us with this final thought. We started by talking about friction being the #1 cause of delay in science. So, if a system can really, truly remove that friction, the wasted time, the crazy costs, the dead ends, it begs a much, much bigger question. What breakthrough is just sitting there, right now, waiting for us to find it on the other side?